Let's get started. So just real quick, as she said, I built a bunch of APIs. I actually built a bunch of LAMP stacks for these companies, and which are basically your old-fashioned monolith MVC kind of web servers and those types of applications, because that's what they were running at the time over at Yahoo and Ames. And now I do cloud native development, which is the real word for serverless, as part of CloudReach, and I do it for all of CloudReach's clients. So the important thing is, what is serverless and what is it really? According to the Serverless Stack, which is a book I highly recommend if you're interested in this sort of topic, it's an execution model where the cloud provider is responsible for executing your code by dynamically allocating the resources, which is all great and everything, but that's just way more buzzwords. So what does it really mean? What it really means when everyone starts getting their hands dirty with it is that it's an event-driven application design that uses the cloud-native services. So if you are using any of these services like AWS or Google Cloud Platform or Azure or IBM Cloud, you would just be using the services they provide to you, such as BigQuery or Lambda or API Gateway or whatever that you need, instead of building out a virtual machine in order to run your code. So the reason why this is important is that using the services that are already provided to you, it's faster to do it that way. When you want to prototype something fast, you want to see where all of the resources are going to get laid out, and you're just one of these people that you learn better as you build, then using cloud native services makes it a really cheap thing to do, because then all you do is you spin up your account and then you just start plugging and connecting things away until you get something that works. So it's very fast to prototype, and because you're using the cloud services backbone, then it's also fast to run. And because you're using cloud services, it's optimized, which means every cloud service provider, it's in their best interest in order to do things quickly and securely. So whenever they make an improvement on their service, especially with reInvent literally next week, all of the improvements that they make for their infrastructure, you get as they roll it out. So you don't actually need to do minor updates if you're using like their base package. If you're using Amazon Linux, for example, as soon as that gets updated, all of your stuff gets updated. And it scales automatically, so you don't have to build in an orchestrator. An orchestrator is basically this virtual system that controls a bunch of other virtual systems in order to run code in a way that where you can either get more instances or more resources as you need them. When you do things in a cloud native manner, then it does all of that automatically. It will spin up your code once when you call it the first time, and then just create new instances of that every time the same piece of code is invoked. So it does what we call horizontal scaling, because it doesn't change the number of resources in there, but it will just keep opening up more and more and more and more every single time that it gets called to a point. I don't know what the limit is, because that's one of those soft limits that they hide, but it is in the thousands. And it's pay as you go. So this is really important if you're learning or if you're a startup. Or if you're in development. So what this means is that every time it invokes the function, you pay for the resources you use at that exact moment until whatever you're doing is done and it spins down. When you're not using it, this is, again, important if you're a startup and important if you're learning, and you want to spend those spare cycles doing these weird non-productive times like sleeping, eating, and time with loved ones, then you don't actually pay for that. You don't pay for this always-on service that you would be if you were spinning up a full virtualized server and just letting that run all the time. If you don't know what your usage is going to be, then it's great for that, because if you have a spike, the auto-scaling covers that. And if you have a lull, you don't pay for the stuff that you're not using. And also, as I said before, all the cloud providers provide basically the same services. So if you feel like you can't go explore other services in another cloud, you can actually, and you already have, your work is either with AWS or Azure, and you just wanted to learn more with that, you can do these kinds of exercises and development inside of that cloud. The table that I put on the slide right now was from a previous presentation I did on cloud APIs this spring, and it shows the similarities between the services. So you have AWS, GCP, or rather Google Cloud Platform, Azure, and IBM Cloud. For AWS, you have to do virtualized API endpoints. You have API Gateway. For Google, you have Apache. For Azure, you have API Management. And Google Cloud, for IBM Cloud, I believe it's called, it's also an application management layer. In order to do computes, like running small pieces of code, we have that called functions as a service. In AWS, it's called Lambda. Google, it's called Google Cloud Functions. In Azure, it's Azure Functions. And in IBM Cloud, it's just called Cloud Functions. And if you need something that's more robust, that does have registration that you can manage with it, you have AWS's Elastic Container Service, and Google Cloud, you have Kubernetes, and in Azure, you have Azure Container Service, and you have the IBM Cloud Container Service. There are a bunch of other services that all of the cloud providers have that all match together. The point is that if you can design it in one, it's very likely you can design it in the other one, and you should be able to pick the one that has the most built-in services that's very much like what you want to do, and be able to start there. So usually when I was in the public sector and I wanted to onboard new technology or learn new things, I always had to find out what the counter arguments were first, especially in the public sector where budgets are done at the beginning of the year and not as you buy stuff. Then you have to prove a business case immediately. And if you have a history of trying to learn too many new things and bring them in, or you've put in a lot of resources into trying to learn one language and then have the project shift and go into a different direction, then that makes it very hard to make the case. It's like, this is a thing that I want to learn. So we're going to be going over those arguments and why they shouldn't be a hindrance on anyone trying to learn how to do things in the cloud. I used to think this argument was out of date, that there were still servers, but when I came back from Serverless Conf in October, we were still arguing about the fact that it did have servers and how much serverless tech was too close to having servers and which one doesn't. So the main argument is that it still has servers, even though it is called serverless, which is why a lot of times we will just call it cloud native. The reason why we call it serverless is because we don't have to spin up a virtual instance and you're not paying for that 24/7 always on kind of capability. However, it is, at the end of the day, a computer on the internet, and all computers on the internet are known as servers. That's how it is. And people who tend to get bogged down in the terminology of it are just looking for reasons to argue about it. because the one thing that engineers love doing is arguing about the semantics of what our technology actually is supposed to do. So this is my wonderful visualization of the difference between a serverless and serverful environment. On the left, they're both engines. The only difference is that the one on the right has a cap on it. So you see less of the parts inside. You still see a lot of parts, but you don't have to see the, I don't know, cylinders, pistons. I'm not good with cars, to be honest, because I'm only interested in what makes the car go and whether or not it's broken and if it's going to tell me it's broken. There is an argument to be made that I know a lot of people in this industry really like playing with their cars and tweaking them, but it just like when you're dealing with computers, if you're too deep in the details and you're trying to make those really minute kind of performance tweaks, then chances are you actually know what you're doing. So you wouldn't get caught in this kind of no control environment to begin with. So either that or it's your job and you already know what you're doing. So either way, for the general public, people who just want to be able to build their applications, we don't need to know the hidden secret sauce of the way it does routing and networking and stuff like that. The cloud will take care of that for us, just like the car dealership will take care of the engine, and we can only hope that it'll tell us if it breaks. Another one is that I don't have time to learn because time is as much of an investment in learning technology as money is. So when you're trying to learn a new language and let's say, and this has happened in a lot of in enterprise situations where they've pushed their engineers to learn Python or Node. Those are the two biggest, or Ruby. Those are the biggest languages that people have been pushed to go into. So if you were pushed to learn Python before, that example is on the left. It's a simple hello world. It literally just prints hello world when you run the script. On the right is how you would do it in a serverless fashion. So what happens is that it gets built into this image that gets run by the cloud provider. So you're not actually running live code as you type it, but it will save it and rebuild the image every single time it saves. So you should be okay once you get everything running. That shows what the difference is, where instead of just printing the line, we're building it into a handler function, which will give us an expected return type and basically do the same code. So in order to build that code into a function, it's going to take less than 2 minutes. And the only reason why it takes 2 minutes to do in this demo is because I messed up the first time, and I'm going to show you how quick it is to delete it. So all of that is going to take a couple of minutes. So in AWS, all you have to do is you go to click a function, and we're going to build a name. I'm actually going to choose the wrong runtime. I didn't do it on purpose, but I just decided to keep it in because I think knowing how things break and what to look out for is very important. So you choose your execution rule, which is how the cloud is going to know how to run your code. And then right now it's building that function. It'll build you a base function that has a very hello world type template in the code. And then you can make any adjustments from there. And since I made it with Node instead of Python, and my previous example was in Python, I just deleted it, and that's how quickly it took to delete everything. So now we're going to go through this process again, click create function, and then I'm going to take a little too much time trying to figure out what I should name the function, because if I don't have a built-in nomenclature, I end up this being one of those details that I fixate on. So we're going to hello Python. We're going to choose the appropriate runtime this time. Choose our execution rule again, and then we're going to build it. Right now we're at 1:30. even with the deleting of the previous function. So see, all of that did not take that much time to figure out, and it wasn't anything super complicated. You just follow the steps as it's described in the console, and then we drop our example code inside, and then it'll do exactly what we described it doing before, which is building a little image and then running that code. So we're going to print out the words hello world. And then we're going to build a basic test event, which is also why these doing it in the console is pretty interesting, because you can build the test events inside. So I'm just going to take all of the arguments out and run the test event. There you go. And now it not only returns what we expect, but it also prints out the line, and you can see the output of the either in the logs or it has a little output printout, and you can see it work. So all of that, even with the testing, took 2.5 minutes. So if you can find the time to learn a language, then you can actually use that time to also learn cloud, as you can use the cloud service to kind of help you work through building it in an actual, in something that's a little closer to a non-local environment. This is kind of the hardest one to deal with, especially dealing with either public sector, slow-moving embedded industries, that sort of thing, is that we may not use it. And that's fine. If you end up going through all of these steps and not using cloud native services, it still helps you, because a good engineer will actually know a good application design. They will know how to build these things using what's provided and doing it in a way where we make sure that there's proper testing, proper monitoring, proper logging, all of the things that we need in a basic application, except we'll also now know how to do it in the cloud. So you learn a large amount of the services that the cloud can provide, and you learn it in a much more intimate and contextual sort of way. So not only you know how to do things like how to set up queues and all this other stuff, but you know why that's important and any of the pitfalls you may run into. And knowing that will actually give you a better perspective when you go back and you end up going back to monolithic engineering, or you start thinking about doing microservices. It gives you a better understanding of why we have to do things in a certain way, and probably better ways of doing it. Now, serverless is still too new. It's less new now than when I thought of this argument a year ago, but you will still run into this, especially if, again, embedded industries, public sector, and anytime you have to do business case arguments prior to actually building a POC. The good thing about serverless is that the newness helps. It still has features of a mature community, so it has, for all of the services, they are all fully documented. It's a highly collaborative environment, so you can join any number of tech Slack networks. There's usually a serverless channel where you can get help. You can join the channel for the Serverless Framework, which I will get into later, where all of the people who use that framework also are very hands-on with cloud native services, and they're always there to help. Also, because it's new and the barrier to entry for being able to onboard all of these skills is so low, that means there are fewer gatekeepers. And I went into the industry way back when you could still pick a language and kind of know exactly who that type of person who was using it and kind of guess what they look like and how they acted. Because a lot of the way services are used and can cover a variety of industries and different different levels of development. So you can go from front end to back end to DevOps to design to networking, because it touches all of these parts of getting an application off the ground. There is no single type of serverless engineer, and that means there are fewer gatekeepers. There's no one going to say, hey, that's not the way you do things because the rest of us do it this one particular way. It's a lot more inclusive and welcoming than that, and everyone I've run into has mostly been very able and very willing to help. And because it's new, if you've been in the industry for a long time, it would really benefit from having experienced engineers start building this way, because you start bringing in things like best practices and good design. Every amount of growing tech needs guidance on how to be able to do things the right way. Not that there is a wrong way of doing it, but ways that are robust and catch errors and are secure. And when people are new and they're learning things really quickly, those are the types of things that fall away immediately. If you've been in this a while, one of the first questions you'll ask is, when trying to learn anything, is like, how do I know that this didn't work? How did I know this broke? Where are the alarms? Where are the logging? Where does all of this go? And even basic questions like that, it helps having more mature engineers go into there. So serverless best practice as a whole are still being defined. Because it touches so many different sections of development, there are overall best practices, but they're also starting to emerge more specialized versions of best practices. Like there's a list out for high performance serverless engineering and another one for security best practices. And this is where like I said, that having a more matured engineer come in and being able to look at this, if you can help define those, it really helps out the community as a whole. But we're going to go over real quick just general rules on when you're doing things in a cloud native way, how to be able to build that out. You have to assume everything is going to be stateless, and you're going to start out thinking asynchronously. So you can't think of everything going in a serial manner, even though there are ways of handling that now. When you start your designs, you should think of the overall whole as being asynchronous. There are going to be parts that you can manage with either state machines or transactional tables to be able to simulate a session, but those will be considered single systems within the entirety of your serverless deployment. All of your deployments, deployment parts, I should say, should be task focused. So everything that you build should just be doing that one thing. So lambdas generally shouldn't call other lambdas that are shared between services, and different logic should be handled with different functions. So you don't want to overload too much trying to get one entry point. You can have one lambda catch a bunch of inputs and data, and then be able to parse out the metadata from it and decide where it goes and put in an appropriate queue after that. But for the most part, you don't want to have one lambda handling as much code as a full application. And the data shouldn't rest. You shouldn't be like, even though we all kind of do it sometimes, you shouldn't be like hardwiring in timeouts in order to slow the process down. The data should be moving, and there should be considerations given for when you are waiting for another state to finish. That's when those state machines and transactional tables come in, where you can actually manage things better that way instead of just having them wait somewhere in a holding state. So this is At the end of the day, after you do your deployment, this is a simplified version of a system that I built, which is an ETL, which basically moves data from point A to point B. So that's what this architecture diagram would look like, and that's one of the things that scares a lot of business decision makers, because instead of having something clean, like this would generally be considered one server. Now you have a bunch of services with its own routing and its own security that they have to worry about, and having one piece turn into 1, 2, 3, 4, 8 pieces, that can be a little scary. It doesn't need to be, but it's one of those knee-jerk reactions. So we're going to show exactly what that's going to look like. If you took a monolithic application, a simple one, and turned it into a serverless application, because doing these types of spinouts is actually a very common use case. And before I get started, I should preface that what I actually ended up doing to be able to do this demonstration is that I took a serverless application and I shoved everything into a computer, into a monolith, and then I broke it apart again. So we're going to see kind of a two-way system going on here. So I'm not sure who's familiar with what this image is, but I did not make this, I promise. This is from the AWS, their code examples, because they built their entire serverless tutorial library around the idea of an application where you can order unicorns for your unicorn needs, kind of like Uber for unicorns. And they call it wild rides, and if you go through one of those tutorials, you're gonna see this image a lot, and it really burns into your brain. So the concept, again, is basically Uber for unicorns. So we have to decide what those application requirements are. We need to maintain a database of unicorns and their states. We also have to allow user authentication. We have to maintain a database of users. We have to maintain a history of actions of those users and allow users to order unicorns. That seems simple enough on the face of it, so we'll see how that works out. If we're going to do a basic application diagram, it would be this type of application where you have the user going into the web server, going through authentication, application, database, web server. Standard 3-tier application. But if you notice the difference between this and the previous diagram, it's much cleaner because there are only 2 icons on it and a bunch of words. And if you're trying to explain this to a business decision maker, it is way easier to get away with this because they see one thing that they're paying for. However, that thing that they're paying for is a lot. So if you just got a monolith, this is basically an always-on Linux T3 extra large. So just something that can manage the traffic of 100,000 users. It would be about $250 a month, which is not great. And it also does not include auto patching. It also doesn't include scaling. And again, it's always on even when it's not being used, even though when it's not being developed on, and that's not great. This is the serverless design from that exact tutorial. So if you notice, we turned one icon into 1, 2, 3, 4, 5, 6 icons. So that's where that knee-jerk reaction comes in, because they see, oh no, now I'm paying for six services, paying for 6 whatevers, and that's just going to be more complex when we're trying to do cost management. It's not, and I'll show you why. These services do different things. Amplify takes the code that you check in to get, and then it just builds into an S3 bucket and pushes that front end out. Cognito is AWS's Active Directory service, so it allows you to authenticate, or it also acts as a proxy if you wanted to authenticate using social services or SAML or whatever you need. And in order to run the backend code, it's going to be decoupled using API gateway, and Lambda as its computes, which is that functions as a services I talked about, and DynamoDB, which is their NoSQL offering. But even though it's more services, it actually looks much cleaner because now you know exactly what kind of activity is going where. This is actually much less money also. Again, super important if you're learning, if you're developing, or if you're a startup. It's also great if you're an enterprise and the way your company makes its money is on efficiencies. Then this is great because every time you onboard more data, the cost doesn't start spiking out. So we're looking at, this is kind of the standard model. This is from a website called Serverless Calc, which will, depending on the cloud you choose, it will tell you at the bottom how much it's going to be to run that much memory for an X amount of time over these functions. And for that, even at the highest cost, which is Lambda, would be less than $4 for a month, which is much better than $250. And breaking that down, that means that's 2 million functions are less than $4. That API gateway is free for the first 330 million requests. Cognito is free for the first 50,000 monthly active users. DynamoDB is $5 for the first 350,000 reads and 350,000 writes. That's something you do need to monitor though, because it considers them two different things. So if you're doing a lot of callbacks, then you can start picking at that quickly. No, obviously not quickly to blow your costs totally out of control if you're in development, but if you are in that enterprise layer and then you are suddenly onboard a lot of data that's highly interactive, then you may need to go, that's the part I would advise that you start looking to massage. And Amplify does 15 cents for every gigabyte served. So again, great if you need to scale or if you're just doing development. One of the issues that we run into with trying to convince people to go cloud native is that there are a lot of tools that we build when we build applications that we know just intuitively that we need. Again, logging, monitoring is a really big part of that, version control, all of this other stuff that we bootstrap into all of our processes and applications, that when we're asked to do it in a way that is not just one monolithic code base, then it starts getting a little sticky. So there are a lot of these problems have already been solved. So let's take a quick tour over what those solutions are. So for version control, first step of any project, I would always advise you open up a repo, even if you end up not coding a word of it, just because it keeps the worst from happening, such as, if you're in my case, a toddler tipping your computer over, then dumping a cup of water into the fan, and you lose everything. This will prevent that from happening. But because we're no longer dealing with a single code base being dumped into one server, we need to find a way to manage these services using code. The answer for that is infrastructure as code, which is a way of using either JSON or YAML definitions in order to build cloud-native resources. And all of these definitions can be tracked in Git. One of the industry standard versions of this is Terraform. This is actually not built using either YAML or JSON. It's built using their own proprietary HashiCorp language. It's really good at deploying cloud services. It's less good with, it makes a lot of the serverless interaction really complicated sometimes. And every time you change Lambda code, you need to redeploy. That makes it a little bit difficult, But if you wanted to start standardizing the way your infrastructure was built, this is the way to do it. It's the way everybody else does it. It also lets you template things in an easy way so that you aren't like manually handling stages and being able to point to the proper things. Another version is Serverless Framework, which uses both JSON and YAML. And it is good at deploying a lot of cloud-native services. Some things you need to build manually or through CloudFormation. And the thing is, when you start deploying through the Serverless Framework, it will, if you use AWS, it'll use CloudFormation. And if you use GCP or Azure, it will build those stack definitions there, as opposed to Terraform, which will call API calls and start building them without definitions so that you can't just redeploy from the console that way. And all of these definitions can be checked into Git, and this is what one of those files would look like. So what I personally like to do is I use both. For things that either can't be built in serverless easily, or things that are going to be shared or managed by a security team or a different infrastructure team, I build those resources in Terraform. When we're talking about things like lambdas and event triggers, all of that stuff I build into serverless, and having this hybrid type of build out is actually very common, and it is considered a standard way of building. Now, here's where we get into the less optimized version of the cloud, where when you use the cloud, you are using whatever the cloud provider gives you, and sometimes what they give you isn't what you need. It's basically dealing with any computer that comes out of the box. If you just bought it from Best Buy or something, then you have to install more stuff. It's the same thing with these visuals, right? With these virtual machines and these containers. Not everything is going to come out easily. For some things that can be built just by adding new libraries, you can do that in AWS. It has ability to create a shared library called a layer, where you create it, you just add the pathing, and then it will add this screen cap uses Pillow, but I've also done it with PyYAML, because YAML's not a built-in library. I don't know why, but it isn't. Or you can build in containers. I can literally talk about that for 25 minutes, but I won't. So here, there are just things to know that if you were going to do this in any other scenario, you would also just build it into the deployment package, where you would just zip all of your code up and then just put it there. But but when you do shared libraries, you just have to remember they are still part of your deployment package, and they still have to respect the limits set by your provider. So in AWS, that's 250 megabytes. If your library is too large and you have too many node modules, then that will cause it to break. Google also has the ability now called Cloud Run. This was released a couple months ago, where you can create a custom container and you can run it as a function, which is great, especially if you have to use blessed containers from your security group, or it doesn't have the thing you need, and you just need to build out your own runtime in a way where you know you can store it in an easy way using Docker files. It's always Docker files. So they allow you to do that. Azure also has a version of this called Cato, which is a Kubernetes cluster made to act like a serverless VAS. That one is a lot more complicated and a lot closer to the orchestration part. And the more you move closer to orchestration, the less optimization you're going to have. And speaking of that, if you want a full service end-to-end custom solution, then you are basically building your own cloud at that point, which is a thing you can totally do. You can do it. If you use OpenWhisk, you can either, it uses a containerized system and its own custom message queue so that you can build things the way you want it, using the services that you want, using the languages that you want, because you are custom building everything, which is great if, again, you're on a enterprise system and you need everything done to in a very specific specification. Again, this is a lot of money to do, and the more customization you do, the more money it costs, the more engineers you'll need to be able to maintain it, the more expertise that you are required, and domain knowledge that you're going to need in order to maintain it. So these are just trade-offs you need to think about if you plan on going this route. Monitoring is important. I always say it's important, but no one believes me until something goes down. So monitoring is important because you need to be able to prove things work end to end, and that if it's not your fault, something broke. You have to be able to show someone who may not be technical where an error lies and why it happened, and being able to fill out one of those called root cause analysis reports, which I've filled out many times in this past year just to prove that it wasn't something I built. There are a lot of services for this, and every cloud service provider has its own built-in monitoring stack that some of them are more useful than others. Some of them are even more integrated than others. In AWS, it's called CloudWatch. It's not end-user friendly. It builds things the way they expect engineers to want to use them, but it doesn't come with things like end-user friendly URL, so you can't send it in an email. And it requires a lot of instruction and understanding on how to get from that link to the chart that you want. It also requires a lot of manual configuration and instrumentation. So they have some basic metrics like how many times errors pop up and stuff like that. But if you need anything that isn't exactly how the container is running, then you need to instrument that stuff in. GCP's dashboard is much better looking, and their UI is great. And it's one of those things where this is actually Apogee. Apogee is a company that they bought, and theirs is decoupled from the GCP service so that you can actually use Apogee with either Azure or AWS if you wanted to. It also comes with pre-built dashboards. It also comes with custom dashboards that you can send to business decision makers so that they can be able to understand what the systems that they own are doing, and being able to contextualize that in a way that makes a lot more sense. Azure also has, the thing that Azure has over all of the cloud providers is the fact that they spend a lot of money in UI, and they have basically owned the enterprise space for a very long time. Because of this, they know what it takes to get things approved in a business process, so they know exactly what kind of dashboards and monitoring things should look like, so they're not all just numbers and graphs thrown at you. They tell you exactly the kind of information you need to know. And also Azure DevOps is actually really good for being support friendly. So if you had a separate support team, they're able to look to drill down their metrics in a way where they don't have to have intimate knowledge of your system to be able to do it. There are also third-party tools. Epsagon creates shared library tooling so that you just drop the library into your application and it'll do all the tracking for you. And Datadog will scan all of the logs out of an S3 bucket. So long as you're dumping all of your logs in one place, it can do its machine learning magic and be able to show all that stuff for you. So this one is Epsagon. Like I said, it's a really great dashboard, and it's really easy to get to the thing that you can show is broken. Okay, so And then we come back to the question, is like, now that we have all that and we have all of the stuff that we need in order to make it clear exactly what needs to be in a serverless application, what if that's still not enough? I still can't get this approved, or it doesn't have the kind of horsepower that I require. I can't get this to security. They look at this and tell me no. What do we do? This is how you roll back a serverless deployment. You take all of your little bits of code and your containers, and then you put into a container orchestrator, and then it will do a lot of the same functions. And that's how you can maintain that scaling, that auto scale out that you need, that was still in there, and you can still get, because you're using custom containers, you can probably get more of the horsepower out of that. Unfortunately, if you're using other people's software, like off-the-shelf software, I believe they call it, where, let's call it SharePoint or WordPress or whatever, that's something someone else built, and you're just loading it into a server. You can't get away with rebuilding that. Same thing is when UI is required, you either need a full container to be able to run that front end, or you need a server. You need something to be able to run the thing, to be able to reach to that backend. Serverless is a really great migration if you're dealing with things that you already own and you want to own it. If you just want to pay for SaaS or exploit those, then you can use a minimal amount of serverless to connect to SaaS. Or if you just want to buy up software, then you have to use a virtual machine, because that's the way they want you to install it. So we're gonna wrap this up, and let's go over the things that we learned. There are always going to be arguments. The arguments that keep you from serverless are the same arguments that keep you from learning any kind of new technology. They aren't always deal breakers, but there's also ways to roll back if you need to. A good serverless practice is always good design practice, and that design is going to keep data moving one way or another. And we saw how to do what's basically a strangulation migration, where we turn a monolith into a serverless application. And we saw a bunch of post-dev bootstrapping work, including monitoring and version control. And again, when it doesn't work, you can always scale back. The moral of the story is that good code is good code. If you build something well, then you can use whatever you built, the designs and the code, in a monolith, and you can also use it inside of a microservice environment. If you want, I'll have resources later. I'll put them up on my Twitter, and I talk about this stuff all the time. And if you look up any of my other talks, then you will see me go into these topics in much more detail. And Minka, I think I've wrapped up.